The star you're about to look at may already be dead. Not dying. Dead. 640 years ago, on the shoulder of the constellation Orion, a giant more than 1,000 times wider than our Sun began pouring out the light you can still see tonight, a single orange ember in the winter sky. But that light is centuries old, and the star that sent it is in the final moments of its life. Its core is turning to iron, the one element no star can survive, and its collapse could come tonight or 100,000 years from now. No scientist alive can tell you which. Betelgeuse is very nearly 1 billion times the size of our Sun. It is about to explode, and the flash of its death may already be racing toward us through the dark. If a mystery like that pulls at you, like this video, and subscribe to the Sky Lab, where we follow the biggest stories in the sky. And tell me in the comments, if Betelgeuse exploded tonight, would you want to know, or would you rather be surprised? Now, let's get into it. Part 1. The Ember on the Hunter's Shoulder. There is a star above your head tonight that may already be dead. Not dying, not fading, dead. Gone in a flash of light so violent that it briefly outshone the entire galaxy that made it. And the strangest part, the part that should stop you cold, is that we would have no way of knowing. Because the thing you can walk outside and see right now, the orange point of fire hanging in the winter sky, might be nothing more than an image, a photograph in light taken 6 centuries ago, still travelling toward your eyes, showing you a star that no longer exists. We tend to think of the night sky as permanent, the same stars our grandparents saw, the same ones the ancient Greeks named fixed and patient and eternal. But that permanence is an illusion, and one star in particular is about to shatter it. This is the story of a giant in the final moments of its life, a star so enormous that our entire solar system could vanish inside it, a star that has already begun to come apart and that could explode tonight, or 100,000 years from now, and no scientist alive can tell you which. Its name is Betelgeuse. Step outside tonight once the sky is fully dark and look up. Find the constellation Orion, the hunter. He's one of the easiest shapes to find in the whole sky, because of his belt, 3 bright stars in a short, straight, unmistakable line. Almost nothing else in the heavens looks like that. Once you have the belt, look up and to the left, to the point where the hunter's shoulder would be, and there you will see it. A single point of orange fire burning quietly, patiently in the cold black between the stars. That orange ember is Betelgeuse, also written in the old catalogues as Alpha Orionis, the brightest star of Orion. And it is not like the white and blue points scattered around it. Those burn cold and clean. This one burns the colour of a dying coal, the colour of rust, the colour of fire just before it goes out. That colour is not an accident. It is a symptom. It is the first clue that something is very wrong with this star, and we will come back to exactly what that colour is telling us. Betelgeuse hangs roughly 640 light-years from Earth. Try to hold that number in your mind for a moment, because it matters more than almost anything else in this story. A light-year is the distance light travels in a single year, moving at the fastest speed the universe allows, about 6 trillion miles. And the light now entering your eyes from Betelgeuse has been crossing that emptiness for around 640 years. It left the surface of that star before Shakespeare was born. It left before the printing press changed the world, before Columbus crossed the Atlantic. Kings and empires have risen and fallen in the time it took that single beam of orange light to reach you. And the star that sent it may no longer be there at all. I want you to sit with that idea, because everything that follows grows out of it. When you look at Betelgeuse, you are not looking at a star. You are looking at the past. You are looking at old news delivered slowly, one photon at a time, across a gulf so wide that the message and the messenger have long since parted ways. To understand what Betelgeuse actually is, you have to do something difficult. You have to forget everything you think you know about size. Our sun feels enormous to us, and it should. It is the largest object most of us will ever perceive with our own senses. More than 1 million Earths could fit inside it. It holds 99.8% of all the mass in the entire solar system. Every planet, every moon, every asteroid and comet, all of it together is a rounding error next to the sun. When you stand in sunlight, you are being touched by an object so large that the human mind cannot truly picture it. And yet, next to Betelgeuse, Our sun is a spark, a pinprick, almost nothing at all. Let me try to make this real for you. Imagine we could reach out and pluck our sun from the center of the solar system, lift it out like a marble, and drop Betelgeuse into the hole where it used to be. What would happen? The surface of Betelgeuse would not sit politely where the sun once was. It would come rushing outward in every direction. It would swallow the orbit of Mercury in an instant. Then it would reach Venus and swallow that too. Then it would reach us. The Earth, our whole world, everything that has ever happened in human history would be somewhere far beneath the burning surface of this single star. And it would not stop there. It would roll on past the orbit of Mars out into the belt of asteroids, its outer edge reaching hungrily toward the orbit of Jupiter itself. Everything you have ever known would be inside that star, and the star would barely notice. That is the scale we are dealing with. Betelgeuse is somewhere between 700 and 1,000 times wider than our Sun, and by some older measurements as much as 1,400 times wider. When you count it up by volume, by the actual amount of space the star occupies, you arrive at a number that stops making sense. You could pour hundreds of millions of suns into Betelgeuse. By some estimates, very nearly 1 billion suns could vanish inside it and leave no trace. 1 billion. Take the brightest, most enormous object in our sky, the sun that gives us every day and every harvest and every living thing, and understand that you would need 1,000 million of them to fill this one red star on the shoulder of Orion. The distances inside it are almost impossible to describe. Light, the fastest thing there is, the thing that crosses from the sun to the Earth in about 8 minutes, would take hours simply to travel from one side of Betelgeuse to the other. If you stood on some imaginary platform at its center and switched on a lamp, the far surface would not know for the better part of a day. Let me give you one more way to feel this, because the numbers alone can go numb after a while. Imagine you could board a commercial jet, the kind that crosses an ocean, flying at its usual cruising speed, and you set out to fly all the way around Betelgeuse, one full loop around its middle, the way you might circle the Earth. To circle the Earth in that jet takes about 2 days. To circle the Sun, that same jet would need around 6 months of continuous flight, and to circle Betelgeuse, that jet would have to fly without stopping, without landing, for something on the order of 600 years. 6 centuries of continuous flight just to go once around a single star. Generations of pilots would be born, fly their whole lives and die, and their grandchildren would still not have completed the loop. That is not a distance the human mind can truly hold. It is a scale that belongs to a different order of reality entirely, and yet it is real, and it is hanging in your sky tonight. A single object so large that our fastest machines would spend centuries just tracing its edge. And still, remember, this Titan holds only about 20 times the material of our Sun. All that width, all that impossible circumference spread across so little mass, which tells you just how thin and stretched and swollen this dying star has become. This is not a star in the way the Sun is a star. This is a slow, brooding red world of fire, so large that it plays by different rules of time and space than anything we will ever stand near. And here is the twist that turns wonder into dread. All of that size, all of that impossible scale, is not a sign of strength. It is a sign of collapse. It is a symptom of a star that is running out of time. Because for all its width, Betelgeuse does not contain 1,000 million times the material of the Sun. Its mass, the actual amount of matter it holds, is only about 16 to 19 times that of the Sun. Think about what that means. You have a star spread across 1 billion times the volume, holding barely 20 times the material. It is stretched impossibly thin. The outer shells of Betelgeuse are more tenuous than the air you're breathing right now, a red fog of gas so faint that in most places you could fly through it and hardly know it was there. The star has swollen and bloated and puffed itself outward to a monstrous size, and that swelling is one of the surest signs in all of astronomy that a star has entered the last chapter of its life. We measure that in another way too, in colour and in temperature. The Sun's surface burns at around 5,500 degrees, and it shines a brilliant white. Betelgeuse burns much cooler, only about 3,500 degrees, and so it glows that low, sullen orange red. In the strange logic of stars, the cooler a star's surface, the closer to death it very often is, because that coolness comes from expansion, and that expansion comes from a core that has begun to change in ways that cannot be undone. The colour you see with your own eyes on a winter night is the colour of a fire burning down. So we have a star of contradictions, impossibly large yet stretched to almost nothing, only 8 to 10 million years old, a mere child by the standards of stars, and yet already old, already dying, already flickering at the edge of its own destruction. Our Sun will live for roughly 10 billion years, and it is not even halfway through. Betelgeuse has existed for less than 1,000th of that, and it is nearly finished. How can something so young be so close to the end? How can a star that has barely existed already be preparing to die? The answer lies in the kind of star Betelgeuse is, a member of a rare and dangerous family, the most powerful and the most doomed stars in the entire universe. And to understand why Betelgeuse is running out of time, we first have to understand why the bigger stars are always the first to fall. Part 2. A rare and dangerous family. Betelgeuse belongs to a class of stars that astronomers call the red supergiants. The name is almost an understatement. These are the largest single objects in the known universe by sheer physical size, stars so swollen that if you line them up against an ordinary star like our Sun, the Sun would be a grain of sand beside a cathedral. They are among the brightest things in existence, pouring out the light of 100,000 suns, and they are, without exception, the shortest-lived stars of all. They are born, they burn like nothing else in creation, and they die young and violently. To be a red supergiant is to have made a bargain with the universe, and the terms of that bargain are always the same: burn brighter than anything else, and burn out first. To understand why, you have to understand what a star actually is. A star is not simply a ball of fire. A star is a battle, a war that lasts for millions or billions of years, fought between two enormous forces that never rest. The first force is gravity, and gravity always wants the same thing. It wants to crush. Every scrap of gas in a star is being pulled inward, toward the centre by the combined weight of everything around it. Left unopposed, gravity would collapse a star into a single point in a matter of hours. The only thing that stops it, the only thing that has ever stopped it, is the fire burning in the core. That fire is nuclear fusion. In the centre of a star, under crushing pressure and unimaginable temperature, atoms are forced together so violently that they merge, and each time they merge they release a burst of energy. That energy pushes outward. It pushes back against gravity, and for as long as the fire burns, the star holds itself up, balanced perfectly between the crush of gravity pulling in and the push of fusion pressing out. This is the secret truth of every star you have ever seen. It is not a fire, it is a balancing act. It is a tightrope walk that lasts an age, and the moment the fire falters, the moment the fuel runs low, the star begins to fall. Now, here is where the size of a star decides its fate. You might think that a bigger star with far more fuel would live far longer. It seems obvious. More fuel, more time. But the exact opposite is true, and the reason is one of the cruelest facts in all of astronomy. A giant star like Betelgeuse has vastly more fuel than the Sun, but it burns that fuel at a rate so ferocious that it makes no difference at all. To hold up all that extra weight, to keep from collapsing under its own enormous mass, a supergiant has to burn its fuel not a little faster, but millions of times faster. It is like the difference between a candle and a bonfire. The candle has less wax, but it can burn all night. The bonfire consumes a mountain of wood and is gone by morning. A star like our Sun, modest and patient, sips its fuel. It will shine steadily for around 10 billion years. A red supergiant like Betelgeuse does not sip. It devours. It tears through its fuel in a cosmic blink, in just a few million years, and so the largest, brightest, most magnificent stars in the universe are also the most doomed. They live fast. They shine like beacons across the galaxy, and they die before stars a fraction of their size have even finished being born. Betelgeuse is only 8 to 10 million years old. If our Sun's entire lifespan were compressed into a single day, Betelgeuse would have lived for barely more than a minute, and it would already be at the very end of that minute gasping. And it is worth pausing on what the surface of such a star is even like, because it is nothing like the smooth, steady disk you might imagine. Betelgeuse has no solid surface at all. What we call its surface is simply the layer where the gas becomes thin enough for light to escape, and that layer is in a state of constant violent upheaval. The outer regions of the star boil like a pot left too long on the stove, broken into enormous cells of rising and sinking gas. But these are not the small, tidy convection cells of the Sun. On Betelgeuse, a single one of these bubbling cells can be larger than the entire orbit of the Earth around the Sun. Picture that. One boiling blister on the face of this star, one single churning cell, wider than our whole planet's yearly journey. These giant cells rise, spill their heat into space, cool, and sink back down, over and over, and because there are only a handful of them at any time rather than millions, they make the star lopsided and lumpy and ever-changing. Betelgeuse is not even perfectly round. It bulges and wobbles and shifts its shape as these titanic cells churn, a restless, heaving, misshapen giant that never holds still. This is not the behaviour of a healthy, settled star. It is the behaviour of a star whose outer shells have swollen so enormously and grown so thin that its own gravity can barely keep a firm grip on them. The boiling is a symptom of a star stretched to the edge of what a star can be, holding itself together by less and less, its surface in perpetual turmoil. And as we will see, that loose grip on its own outer shells is about to become a very important part of the story. But it was not always the red giant you see tonight. To understand the ember on Orion's shoulder, you have to picture it as it was in its youth, because it was something else entirely. It was something beautiful and terrible in a completely different way. Once, long ago, Betelgeuse was a blue star. Not orange, not red, but a searing, brilliant blue-white, the hottest and most furious colour a star can be. In its youth, it may have blazed at tens of thousands of degrees, a savage jewel far brighter and far angrier than the gentle giant we see now. In those early millions of years, Betelgeuse did what every star does at the start of its life. It burned hydrogen. Hydrogen is the simplest element in the universe, the lightest, the most abundant, the primordial fuel left over from the birth of everything. And in the core of young Betelgeuse, hydrogen was fusing into helium, releasing torrents of energy, holding the great star up against its own tremendous gravity. For millions of years that balance held. The fire in the core pushed out, gravity pulled in, the tightrope walk went on. But hydrogen, no matter how much of it there is, does not last forever, and in a star burning as recklessly as Betelgeuse, it lasts a shockingly short time. And then one day, far down in the core, the hydrogen ran out. This is the turning point. This is the beginning of the end for every massive star. And it is worth slowing down to understand exactly what happens, because it is the engine that drives everything else in this story. When the hydrogen in the core is exhausted, the fire there sputters and dies, and the instant the fire weakens, the balance breaks. Gravity, which has been waiting patiently for millions of years, which never tires and never relents, finally gets the upper hand. The core, no longer held up by fusion, begins to collapse inward on itself, and as it collapses, something strange and important happens. Squeezing the core makes it hotter, much hotter. So hot that a new fire can catch, a fire that could not burn before. The helium that had been piling up in the core as the ash of hydrogen fusion suddenly becomes fuel in its own right. At these new, higher temperatures, helium itself begins to fuse, forging heavier elements still, carbon and oxygen, the very elements that you and I and every living thing are built from. A new fire roars to life in the centre of the star. But this new fire changes everything about the star's appearance, and this is the key to the whole picture. When the core reignites with helium burning, it pours out even more energy than before, and that flood of energy pushes on the outer shells of the star with tremendous force. The outer shells respond by swelling outward, ballooning to hundreds of times their former size, and as those outer shells expand, they spread the star's heat over an enormous surface, and they cool. A star that was once a compact, furious blue point bloats into an immense, cool, red giant. That is what you are looking at tonight. When you find that orange ember above Orion's belt, you are seeing a star caught in that transformation, a star that has already burned through the hydrogen of its youth, already reignited with heavier fuels, already swollen and cooled and reddened into a supergiant. The blue star is gone. What remains is the bloated, restless ghost of the star Betelgeuse used to be, wearing the colour of its own dying. And here I have to be honest with you about scale, because Betelgeuse, for all its impossible size, is not even the largest star we know of. If we are being precise, There are stranger and larger monsters out there in the dark. There is a star called Scuti, a red supergiant so enormous that if it replaced our Sun, its surface would reach out past the orbit of Jupiter. There is another, with the plain and clumsy name of Stephenson 2-18, that may be larger still, so enormous that light would take hours upon hours to circle it, a star that pushes against the very limits of how large physics will allow a star to become. Next to those titans, even Betelgeuse looks a little smaller. So why do we care so much about Betelgeuse and not about them? Why is this the star that gets the attention? The answer is distance, and it is the reason this entire story matters. Those other giants, Scuti and Stephenson 2-18, are thousands upon thousands of light years away, so far that they are faint smudges even in powerful telescopes. Betelgeuse is different. Betelgeuse is close. At 640 light years, it is practically in our backyard in cosmic terms. It is the nearest red supergiant to the Earth, which makes it the nearest star of its kind that is going to die. And it is not just going to die. It is going to die in the single most violent way the universe has to offer, close enough that we will be able to watch it happen with our own eyes. Every one of these giant stars is building toward the same catastrophe, following the same recipe, climbing the same ladder toward the same terrible final rung. And Betelgeuse is the one climbing it right in front of us. Because that helium fire in the core, the one that swelled the star into a giant, is not the end of the story. It is only the second step. Helium, like hydrogen before it, will run out, and when it does, the core will collapse and heat again, and a new fuel will catch, and then another, each one burning faster and more desperately than the last, each one buying the star a little less time. The star is climbing a ladder. Each rung is a new element, a new fire, a new stay of execution, and at the top of that ladder, waiting, is a single element that no star can ever burn. An element that does not give energy but takes it. An element that acts like a poison at the very centre of every dying giant, and that will, in the end, be the thing that kills Betelgeuse in less than 1 single second. To understand how a star this enormous can die so fast, we have to look at what is forming right now, far down inside its core. Part 3. The Iron Poison. Everything a star does, from birth to death, is really a story about a single ladder. Picture that ladder standing inside the core of Betelgeuse. Each rung is a different element, a different fuel. At the bottom rung is hydrogen, the first fire, the one that lasted millions of years. Betelgeuse climbed off that rung long ago. The next rung up is helium, the ash of the first fire that became the fuel of the second, the fire that swelled the star into a giant. And Betelgeuse is well past that now too. The star is climbing rung by rung, and here is the terrible thing about this particular ladder. Every single step takes less time than the one before, not a little less, dramatically less. Each rung the star climbs, the clock runs faster, and the end rushes closer. Let me walk you up that ladder, because the acceleration is genuinely frightening. Hydrogen burning in a star like Betelgeuse lasts something like 8 million years. That is the long, stable stretch, the equivalent of a whole human life. Then helium burning takes over, and that phase lasts only a few 100,000 years. Already the clock has sped up by a factor of 10 or more. When the helium is spent, the core collapses and heats again, and carbon begins to fuse, and the carbon-burning phase does not last hundreds of thousands of years. It lasts something on the order of centuries, from millions of years to hundreds of thousands to mere hundreds. The star is falling up the ladder now, faster and faster, and it keeps going. After carbon comes neon, and neon burning in the core of a supergiant might last only about a year. 1 year, a star that has lived for 10 million years, burning a single fuel for as little as 12 months. After neon comes oxygen, and oxygen burning lasts perhaps a few months. And then comes the final fuel before the end, silicon, and here the numbers stop sounding like astronomy and start sounding like a countdown. Silicon burning in the core of a dying supergiant lasts around a single day, maybe 2. A star wider than the orbit of Jupiter, older than the human species by millions of years, and in its final chapter it is tearing through entire elements in a matter of hours. Why does it speed up like this? Why does each fuel buy so much less time than the last? The answer is that each new fuel gives back less and less energy when it burns, while the star's desperate need for energy only grows. To hold up against its own crushing gravity, The star needs a certain push from the core, and as the easy fuels are used up and only the stubborn, heavy ones remain, the star has to burn them faster and faster just to keep from collapsing. It is a creature running out of breath, gasping quicker and quicker, and each breath doing less. The star is not living anymore, it is barely holding on. And I want you to picture the sheer strangeness of that final day of silicon burning, because it captures the whole tragedy of a dying giant in a single image. On the outside, nothing appears to be wrong. The star still hangs in the sky, still glows its familiar orange, still looks, to any observer, like the same patient giant it has been for millions of years. A civilization on a planet somewhere, looking up at it, would see nothing to alarm them. But inside, in the core, the star has become a frantic, roaring, multi-layered furnace, running at a pace beyond comprehension, burning through an entire element in a single day, building iron by the second, racing toward a cliff it cannot see and cannot stop. The calm of the surface is a lie told by distance and time. Beneath it, the countdown has entered its final hours, and the star does not even know. Consider how much is happening at once in those last hours. The star is not burning one fuel in one place. It is running every furnace it has ever lit, all at the same time, stacked in shells. In the outermost regions, hydrogen is still quietly fusing, as it has for millions of years. Below that, helium burns. Below that, carbon. Below that, neon and oxygen, each in its own layer. And at the very center, silicon fuses in a final, furious blaze, dumping fresh iron onto the growing core faster and faster. Every shell is active, every layer is cooking the ingredients for the layer beneath it, and the whole nested structure is tightening and heating and accelerating toward the single moment when the iron core crosses its limit. It is the most intricate and the most doomed machine in the universe, and it runs perfectly right up until the instant it destroys itself. And while all of this is happening, the inside of Betelgeuse is quietly organizing itself into one of the most beautiful and most ominous structures in all of nature. Because the star does not burn all its fuels in one place at one time, it burns them in layers, in shells, nested one inside another like the layers of an onion. In the outermost regions, hydrogen is still fusing into helium. Below that, a shell of helium fuses into carbon. Below that, carbon fuses into neon and oxygen. Deeper still, oxygen and silicon burn in their own furious shells, and each layer surrounds the next, hotter and heavier as you go down, until you reach the very center. An onion of fire, hundreds of times wider than our sun, with each layer cooking the ingredients for the layer below, all of it racing toward a single conclusion at the core. So what is waiting at the center? What is the top of the ladder? What does silicon burning produce in that final day of the star's life? The answer is iron. And iron is where the story turns, because iron is not like the fuels that came before it. Iron is the reason the star must die, and die suddenly, and there is no escaping it. I need you to understand something about iron, because it is the single most important fact in the death of a massive star. Every fuel a star burns before iron, from hydrogen all the way up through silicon, gives energy back when it fuses. That is the whole point. You slam light elements together, they merge into a heavier element, and the reaction releases a burst of energy that pushes outward and holds the star up. Fusion, for every element up to iron, is a gift. It pays the star back. It funds the war against gravity. But iron is different. Iron sits at a special place in the structure of matter. It is the most tightly bound, the most stable, the most settled of all the elements. And what that means, in practical terms, is that you cannot get energy out of iron by fusing it. If you force iron atoms together, they do not release energy, they absorb it, they take. Fusing iron is not a gift to the star, it is a tax, it is a drain. Iron is the one fuel that costs more than it pays, and so when the core of Betelgeuse fills with iron, the fire that has held the star up for 10 million years finally, permanently, goes out. This is why I call iron the poison at the center of every dying giant. It is not that iron is dangerous in the way we normally think, it is that iron is inert. It is dead weight. It is a fuel that will not burn, and once the core of the star has been converted into iron, the star has, without knowing it, signed its own death warrant. The countdown that began with the first flicker of hydrogen millions of years ago has finally reached zero. There are no more rungs on the ladder. There is nothing left to burn. And gravity, that ancient, patient enemy that has been pushing inward for the entire life of the star, is about to win the war it has been fighting since the star was born. For a little while, the iron core holds on through a strange and desperate trick of physics. Even without fusion, the core resists collapse because its particles are packed so tightly that they physically refuse to be squeezed any closer, a stubbornness called degeneracy pressure. It is the last line of defense and it works, but only up to a point. There is a hard limit, a threshold discovered by a young physicist named Chandrasekhar, and it comes out to about 1.4 times the mass of our Sun. As long as the iron core stays below that limit, degeneracy pressure can hold the line. But the shells above are still burning, still dumping fresh iron down onto the core, and the core is growing heavier by the second. And the moment it crosses that limit, the moment the iron core weighs just a hair more than 1.4 suns, the last defense fails completely, all at once, everywhere. What happens next is almost too fast and too violent to picture, but I am going to try to walk you through it, because it is the most extreme event in the physical universe, and it is coming for Betelgeuse. In less than 1 single second, the iron core of the star, an object larger than the Earth, collapses, not slowly, not gradually. It falls inward on itself at speeds approaching 1/4 the speed of light. Something the size of a planet crushes down to the size of a city in a fraction of a heartbeat. The temperature soars into the billions of degrees. Electrons are crushed into protons, and the matter of the core is squeezed so hard that it transforms into something almost unimaginable, a ball of pure neutrons, packed as tightly as the nucleus of an atom, so dense that a single teaspoon of it would weigh as much as a mountain. The center of the star has become one of the strangest objects in creation in the time it takes you to blink. Now here is a paradox worth stopping on, because it sits at the very center of how these deaths work, and it is genuinely counterintuitive. The star collapses inward, and yet the result is an explosion that blasts outward. How can falling in cause a blowing out? For a long time this was one of the hardest puzzles in all of astrophysics, and even now the details are an active area of research. But the broad picture is this. When the infalling outer material slams down onto that newborn ball of neutrons at the center, it hits something that simply will not compress any further. The neutron core is about as dense as matter can get, and it acts like the hardest floor in the universe. The material crashing down rebounds off it, and a shockwave is born, launched back outward against the still infalling layers above. But that shockwave, on its own, tends to stall. It runs into so much infalling matter that it loses steam partway out. And if that were the whole story, the star might simply swallow itself and leave nothing but a black hole, no grand explosion at all. What appears to save the day, what turns a stalled collapse into the most brilliant event in the universe, is those ghostly neutrinos. So many of them are pouring out of the newborn neutron core in such an unimaginable flood that even though each one barely interacts with anything, their sheer numbers let them dump enormous energy into the stalled shockwave from behind. They give it a second wind, they reheat it and push it, and the revived shockwave finishes the job, tearing outward through the rest of the star and blowing it apart. It is a strange and beautiful mechanism. The most ethereal, least substantial particles in nature, the ones that normally pass through everything without a trace, become the hammer that shatters a giant. The explosion is powered in the end not by fire but by ghosts, and the numbers involved break the mind. The overwhelming majority of the energy of the entire supernova, something like 99% of it, is carried away by those neutrinos, not by the light we see. Think for a second about what that ratio really means. Everything you would witness, the star brighter than the moon, the visibility in daylight, the shadows cast at midnight, the weeks of impossible brilliance, all of that is only the leftover 1%, the scraps of the true event. The real explosion, the full measure of its fury, passes straight through the Earth invisibly and is gone before most of us would ever know it had come. The dazzling visible explosion, the thing that outshines a galaxy and lights our daytime sky, is barely 1% of the true energy release. If we could somehow see the neutrinos directly, the supernova would be 100 times more staggering than the already unbelievable light show. For a few seconds during the collapse, a single dying star produces more neutrinos than every star in the observable universe combined. a burst of particles so enormous that even at a distance of hundreds of light years, a tiny fraction of them will register in our detectors and ring the alarm. That is the true scale of what waits inside Betelgeuse. Not just a bright light, but a convulsion of raw energy so total that its faintest byproduct, the sliver we can actually see, is still the most spectacular thing our sky can offer. And all of it, the collapse, the bounce, the stalled shock, the neutrino rescue, the final explosion, unfolds in seconds. A star that took 10 million years to live dies in the span of a single breath. 10 million years of burning, of climbing the ladder, of building toward this, all of it resolved in a handful of heartbeats at the very end. That is the fate sealed inside the orange ember on Orion's shoulder. It is already loaded, the iron is already gathering, the only thing we do not know is the hour. And then the collapse does something extraordinary. The infalling matter slams into that ultra-dense neutron core and cannot go any further, and it rebounds, it bounces. A shock wave born in the very centre of the dying star begins to race outward, and riding ahead of that shock wave is a flood of ghostly particles called neutrinos, an almost incomprehensible number of them, carrying away the bulk of the energy of the collapse. So many neutrinos pour out of the dying core in that instant that they alone are enough to blow the rest of the star apart from the inside. The shock wave and the neutrino flood tear outward, through all those onion layers, through the silicon and the oxygen and the neon and the carbon and the helium and the hydrogen, ripping the star apart from its core to its surface. But here is the detail that I find the most haunting of all. When the core of Betelgeuse collapses, when this apocalypse begins at the centre of the star, the surface of Betelgeuse does not know. It cannot know. The star is so enormous that news of its own death, travelling outward through its layers, takes hours to reach the surface. For a brief window of time, the outer star still glows quietly in the sky, still burns its familiar orange, completely unaware that its core has already died beneath it, that a shock wave is already climbing toward the surface, that the end has already begun. The star becomes, for a few hours, a corpse that has not yet realized it is dead, and that terrible delay is the same reason we on Earth may be looking at exactly such a corpse tonight and not know it either. But we are getting ahead of ourselves, because this whole sequence, the iron, the collapse, the shockwave, all of it is still hidden from us, still locked away in the core where no telescope can see. We have never watched it happen to Betelgeuse. We can only reason our way toward it. Or at least that was true, until the autumn of 2019, when Betelgeuse did something it had never done in all the centuries humans had been watching it. Something that made astronomers around the world stop and wonder if the death had finally, actually begun. Part 4. The Great Dimming. The night Orion looked wrong. In the autumn of 2019, the astronomers who watched Betelgeuse noticed something strange. The star was getting darker. At first it was subtle, the kind of change only careful measurement could catch, the sort of thing that lives in a spreadsheet before it lives in the sky. Betelgeuse is a variable star, meaning its brightness naturally rises and falls over time, so a little dimming was nothing to worry about. Astronomers had seen it flicker and breathe for as long as they had been measuring it. But this was different. This did not stop. Week after week through the end of 2019 and into the beginning of 2020, Betelgeuse kept fading and fading and fading, further than anyone watching had ever seen it go. By the historic minimum, in late January and early February of 2020, Betelgeuse had lost around 60% of its usual brightness. It had dropped to something like 40% of the light it normally gives. Now put that into human terms. This was not a change buried in an instrument. This was a change you could see with your own 2 eyes, from your own backyard, without any equipment at all. If you were someone who knew the winter sky, someone who had looked up at Orion your whole life and always found that bright orange shoulder in the same place, blazing at the same strength, then in the winter of 2020 you would have looked up and felt that something was wrong. The hunter looked lopsided. His shoulder had gone dim. For the first time in living memory, in all the centuries that human beings had been recording the brightness of this star, Orion looked wrong, and the whispers began. Because every astronomer, professional and amateur alike, knew what Betelgeuse was. They knew it was a red supergiant near the end of its life. They knew it was the nearest star of its kind that was going to explode. And now here it was, without warning, doing something it had never done before, dimming as though a light were being turned down, as though something were happening inside it. So the question spread through observatories and universities and across the internet, spoken half in scientific caution and half in genuine electric excitement. Was this it? Was the giant finally dying? Was the supernova, the once-in-a-civilization event that astronomers had waited a lifetime to witness, actually beginning right now, in front of us? Telescopes turned toward Orion. Observing time that had been scheduled months in advance was dropped so that instruments could stare at the fading star. Papers were written and posted almost overnight. Astronomers who had spent their entire careers hoping, quietly, that Betelgeuse might go off in their lifetime suddenly found themselves wondering if the moment had come. The whole world, or at least the whole world that looks up, held its breath and watched a single orange point of light, waiting to see if it would do the most spectacular thing a star can do. But the supernova did not come. Betelgeuse dimmed to its lowest point, hung there, and then, slowly, over the following weeks and months, it began to brighten again. By the spring of 2020, it had climbed back toward its normal glow, as though nothing had happened at all. The hunter's shoulder returned to its familiar strength. The star had not exploded. It had not died. The false alarm was over, and to a casual observer it might have seemed like the whole episode had meant nothing. But it had not meant nothing. It had meant a great deal. Because when astronomers dug into the mountains of data they had gathered while the star was faint, they discovered something almost as remarkable as a supernova would have been. They discovered what had actually happened, and the truth was stranger and more revealing than a simple flicker. Betelgeuse had not been dimming because its fire was going out. Betelgeuse had thrown a piece of itself into space. Here is what the evidence eventually showed, pieced together from telescopes on the ground and from the Hubble Space Telescope high above the atmosphere. Beginning early in 2019, before the visible dimming even started, something violent happened in the outer shells of the star. Betelgeuse, like all red supergiants, has a surface that churns and boils. Its outer shells are broken into gigantic cells of rising and sinking gas, convection cells, each one larger than the entire orbit of the Earth, bubbling up from below, spilling their heat and sinking back down. It is a surface in constant, slow, monstrous turmoil. And in early 2019, one of these upwellings went wrong. A tremendous bubble of hot gas, a colossal mass of the star's own material, was flung upward and outward with such force that it tore free of the surface entirely. Astronomers call this a surface mass ejection. Imagine the star coughing, or heaving, and expelling an enormous glob of its own outer shells into the cold of space. This was not a small event. The amount of material Betelgeuse threw off was staggering. A piece of the star's own body launched outward on a shockwave, and as this immense cloud of hot gas rushed away from the star and out into space, it did what hot gas does when it moves into the cold. It cooled. And as it cooled, the atoms within it began to stick together into tiny solid grains. The cloud condensed into dust. Now think about the geometry of what happened next. This freshly made cloud of dust, born from the star's own ejected surface, drifted outward and happened to pass directly between Betelgeuse and the Earth. It positioned itself by pure chance right in our line of sight, and a cloud of dust does exactly what you would expect. It blocks light. From our vantage point hundreds of light years away, this dust cloud drew across the face of the star like a veil pulled slowly over a candle, hiding roughly a quarter of the star's visible surface from our view. The star had not gotten dimmer. The star was just as bright as it had ever been. We simply could not see all of it anymore, because Betelgeuse had thrown a curtain of its own making across part of its own face. When the Hubble Space Telescope studied the event, it caught the fingerprints of exactly this process. Dense hot material moving outward through the star's atmosphere in the months before the dimming, then cooling into the obscuring dust. Ground-based telescopes with the power to actually resolve the disk of the star, to see it as more than a point, captured images that showed the darkening spreading across the lower portion of Betelgeuse, exactly where the dust was doing its work. The picture came together, and in the years that followed it was written up in careful detail in the scientific literature. The great dimming explained not as a dying breath, but as a surface mass ejection and its consequences. The mystery had an answer. The star had not begun its supernova. The star had shivered, and the amount it shed in that shiver is worth dwelling on, because it was not a wisp. The material Betelgeuse threw off in that surface mass ejection was a genuine chunk of the star's own body, an amount of matter that, by some estimates, dwarfs the kind of ordinary outbursts we see even from our own sun. Our sun sometimes flings out great clouds of plasma in events we call coronal mass ejections, and those can be enormous by the standards of anything human. But what Betelgeuse did was on a completely different scale, ejecting a mass of its own surface so large that it could form a dust cloud, broad enough to dim the entire star as seen from another world hundreds of light years away. This was the star losing a piece of itself, permanently, into space. It did not get that material back. Betelgeuse is, in a small but real way, a slightly different star now than it was before 2019, having thrown part of its own face into the dark. And think about the sheer improbability of us being positioned to see it the way we did. For that dust cloud to dim the star so dramatically from our vantage point, it had to form and then drift into the narrow line between Betelgeuse and the Earth, blocking our specific view. An observer on a planet in a different part of the galaxy, looking at Betelgeuse from a different angle, might have seen almost no dimming at all, because the dust cloud would not have been between them and the star. We happened to be standing in exactly the right place to watch the giant pull a veil across its own face. It was, in a sense, a private show, staged for our particular corner of the sky, and it sent our whole civilization into a frenzy of wonder and speculation for months. But I want to be careful here, because it would be easy to hear all of this and feel relieved, to file the great dimming away as a false alarm, a fluke, nothing to see. That would be a mistake. Because think about what this event actually revealed. It revealed that Betelgeuse is not a calm, steady, unchanging star. It revealed that this giant is capable of violently tearing pieces off of its own surface and hurling them into space, pieces so large they can dim the star as seen from another world. It revealed a star in turmoil, a star under stress, a star doing dramatic and unpredictable things, and that turmoil is exactly what we would expect from a star in the final stretch of its life. A young, stable star like our Sun does not do this. Our Sun has its storms and its flares, but it does not throw off great chunks of its own surface large enough to be seen dimming from hundreds of light years away. That kind of violent instability, that kind of heaving and shedding, is the behaviour of a star whose interior is churning through its final fuels, whose layers are becoming harder and harder to hold together, whose grip on itself is beginning to loosen. The great dimming was not evidence that Betelgeuse is fine. It was evidence that Betelgeuse is restless, unstable, and changing, right now, on timescales short enough for human beings to watch. It was the star flinching, and a star that can flinch like that is a star moving toward the edge. There is more. In the aftermath of the ejection, astronomers noticed that Betelgeuse's normal rhythm had been disrupted. The star has a steady pulsation, a regular swelling and shrinking that beats like a slow heartbeat, over a period of a little more than a year. After the great dimming, that rhythm faltered and skipped, as though the star had been rattled by what it had done to itself, as though throwing off a piece of its own surface had thrown off its internal timing too. The giant had not just shivered. It had shaken itself out of its own rhythm, and it took time to settle back down. And even now, years later, Betelgeuse has not gone quiet. It continues to pulse and flicker and brighten and fade. In fact, in more recent times, the star has sometimes been observed running noticeably brighter than its long-term average, which of course sends a fresh ripple of speculation through the public every time it happens. Is this it? Is it finally going? The honest answer, which we will come back to, is almost certainly not, at least not because of a little extra brightness. But the fact that the question keeps coming up over and over tells you everything about the state of this star. It is not sitting still. It is not behaving. It is a giant in visible distress, doing dramatic things on a human timescale, and every time it twitches, the world wonders if the end has come. So the great dimming, in the end, gave us two gifts. The first was a lesson in humility, a reminder that even a star we have watched for centuries can surprise us completely, can do something no human had ever recorded, and can send the entire astronomical community scrambling to explain it. And the second gift was a question, a much bigger question. one that would take years and an entirely different kind of investigation to answer. Because as astronomers pored over Betelgeuse in the wake of the dimming, studying its rhythms and its cycles with more attention than ever before, they kept running into a second mystery that had nothing to do with the dust at all. There was a pattern in the star's behaviour, a slow, steady 6-year beat that no one could explain. Something was tugging at Betelgeuse. Something was keeping time with it, hidden in the glare. And when they finally went looking for it, they found something that no one had expected. They found that the dying giant was not alone. Part 5. The Companion. Hidden in the glare. For as long as astronomers had studied Betelgeuse closely, there had been a second rhythm they could not explain. The star's main pulse, that slow swelling and shrinking, beats over a little more than a year, and that one they understood. It is the star itself breathing, expanding and contracting as a natural part of being a supergiant. But underneath that main beat, layered on top of it, there was a second, much longer cycle. Roughly every 6 years, the brightness of Betelgeuse would rise and fall in a slow, patient wave. This longer rhythm had a name, the long secondary period, and for decades it was one of those quiet puzzles that sat in the background of the science, acknowledged, recorded, and unexplained. Something was making Betelgeuse brighten and dim on a 6-year schedule, as regular as a clock, and no one could say what. After the great dimming, with the whole world watching Betelgeuse more carefully than ever, astronomers finally turned their full attention to that 6-year beat. And a group of them began to suspect something that, at first, sounds almost too simple. What if the reason Betelgeuse kept time on a 6-year cycle was that something was orbiting it? What if there was another object out there, circling the giant once every 6 years, and its motion was somehow driving the change in brightness we saw from Earth? In 2024, this suspicion crystallized into a real prediction. Working through the old brightness records and the subtle wobbles in the star's motion, researchers argued that Betelgeuse must have a companion, a second body locked in orbit around it, roughly the mass of our own Sun, circling at a distance of only a handful of times the gap between the Earth and the Sun. On paper, in the mathematics, the companion had to be there. But predicting a companion and actually seeing one are two very different things, and seeing this one was going to be almost impossible, because think about the problem. You're trying to spot a single ordinary star sitting right next to Betelgeuse, an object hundreds of millions of times brighter, buried in its overwhelming glare at a distance of more than 600 light-years. It's like trying to see a firefly hovering next to a lighthouse from miles away, at night. The glare of the giant simply swallows everything near it, and yet, in December of 2024, they did it. Using a specialized instrument on the Gemini North Telescope in Hawaii, a camera designed to take extraordinarily sharp images by capturing thousands of fast snapshots and combining them to cancel out the blurring of our atmosphere, a team of astronomers pointed the telescope at Betelgeuse and pulled the impossible out of the glare. On the 9th of December 2024, they captured it. A faint, separate point of light, sitting right where the mathematics said it should be, tucked in close beside the giant. After decades of suspicion and a century of unexplained rhythm, the companion of Betelgeuse had finally been seen with human instruments. It was real. Betelgeuse had a partner. It is worth understanding just how hard that detection was, because it tells you why the companion had stayed hidden for so long. The trouble with looking at anything close to Betelgeuse is that our own atmosphere gets in the way. When starlight passes through the turbulent air above a telescope, it shimmers and smears, the same way a coin looks wobbly at the bottom of a moving pool. That blurring is usually more than enough to smudge a faint companion into the overwhelming glare of the giant beside it, erasing it completely. The trick the astronomers use to beat this is called speckle imaging, and it is genuinely clever. Instead of taking one long exposure, which would gather all that shimmer into a hopeless blur, the instrument takes thousands of extremely short snapshots, each one freezing the atmosphere in a single instant. Then a computer combines those thousands of frozen moments in a way that mathematically cancels out the blurring, reconstructing an image far sharper than any single exposure could ever be. It is like taking thousands of slightly wrong photographs and using them together to build one that is almost perfectly right. And even with that technique, on one of the largest telescopes on Earth, the the companion sat right at the ragged edge of what was physically possible to detect. This was not a case of someone simply pointing a telescope and noticing a second star. This was one of the most demanding observations in modern astronomy, pulling a whisper of light out from beside a scream of it. That is why the companion had hidden for so long, and why its discovery was such a genuine triumph. It had been there all along, circling patiently, driving that mysterious 6-year beat, and it took the very limit of human technology to finally catch it in the act. The astronomers who study it gave it an affectionate nickname. They called it Beetle Buddy. And once they had actually detected it, they could begin to ask what it was, and the answer overturned what most people had assumed. You see, when astronomers imagine a companion orbiting a dying giant like Betelgeuse, the natural first guess is that it would be a corpse. Betelgeuse is old, so you might expect its companion to be old too, and an old low-mass object is often a stellar remnant, the burned-out cinder left behind by a star that already died, a white dwarf, or something even denser, like the ultra-compact ball of neutrons left by a supernova. That was the expectation. The buddy would be a small, dead, dense thing. But it was not. When astronomers followed up with observations across different kinds of light, including ultraviolet and X-rays, they found no sign of the intense high-energy glow that a compact stellar corpse would give off. The evidence pointed somewhere completely different, somewhere surprising. Beetle Buddy is not a corpse at all. It appears to be a young star, a hot, relatively small, still-living star, roughly the mass of our Sun or a little more, unevolved and youthful, the kind of star that has its whole life still ahead of it. A newborn in stellar terms, keeping company with a dying giant. Picture that for a moment. A young star in the prime of its existence, locked in orbit around an ancient monster in the last chapter of its life. It is one of the strangest pairings we have ever found, a fresh star nested against a dying one, circling it patiently 6 years to a lap. And Beetle Buddy solved the old mystery beautifully. Remember the 6-year brightness cycle no one could explain? The companion is the answer. Betelgeuse is constantly surrounded by clouds of dust, the same kind of dust that caused the Great Dimming, dust made from the star's own shed material. And as Beetle Buddy sweeps around its orbit, it acts almost like a plough, its motion clearing away some of that light-blocking dust from between us and the giant, at least along part of its path. When the companion clears the dust, more of the star's light reaches us, and Betelgeuse looks brighter. As the dust drifts back, the star looks dimmer again. 6 years for one full orbit, 6 years for one full cycle of brightening and dimming. The little star circling patiently, sweeping the giant's face clean, and letting it cloud over again, keeping time like the hand of a clock. A mystery that had sat unsolved for decades, cracked open by finally seeing the small companion that had been hiding in the glare all along. But there is a darker side to this discovery, and it is the part that ties Beetle Buddy back into the story of the giant's death. Because this young companion is not in a safe, distant, stable orbit. It is orbiting close, dangerously close, so close that it is moving through the tenuous outer atmosphere of Betelgeuse itself, through those thin, far-flung outer shells of the giant that stretch out for an enormous distance. And when a small object ploughs through the outer envelope of a giant star, orbit after orbit after orbit, it feels a constant drag, a gentle but relentless friction that steals a little of its energy every time around. And an orbit that loses energy does not stay the same size. It shrinks. It decays. The companion is slowly, inevitably spiralling inward. The astronomers who found Beetle Buddy also worked out its likely fate, and it is a grim one. Over the coming thousands of years, that friction will drag the young star closer and closer to the giant, until finally the companion will be pulled all the way in and consumed. Betelgeuse will swallow it. The small, young, living star that has been keeping the giant company, sweeping its face and marking its rhythm, is doomed to be devoured by the very star it orbits, engulfed and destroyed within something like 10,000 years. It is a countdown of its own, running quietly alongside the countdown in the giant's core, and there is a real question of which countdown finishes first, which adds one more layer of drama to an already remarkable pairing. Will Betelgeuse explode before it can finish swallowing its companion, ending the whole slow dance in a single instant? Or will the young star spiral all the way in and be consumed first, merging into the giant, before the giant itself collapses? Astronomers cannot say for certain, because both clocks are uncertain. The giant's death timed only within that huge window of centuries to many thousands of years, and the companions in spiral estimated across a similarly long stretch. The two doomed timescales overlap, and we genuinely do not know the order of the ending. It is possible the giant goes first, and the supernova simply tears the companion apart along with everything else. It is possible the companion is drawn in first, its addition of fresh material even nudging the giant's own evolution in some small way. Either way, the pairing does not end well for the smaller star. There is no version of the future in which Betelgeuse survives. There is something almost tragic in picturing it. Here is a young star, roughly like our own sun, the kind of star that, given a quiet and ordinary life, might shine steadily for 10 billion years, might warm planets, might even, on one of those planets, allow life to arise and flourish, the way our own sun has. And instead, by the accident of where it was born, this young star finds itself locked in a doomed orbit around a dying Titan, dragged a little closer with every lap, its whole enormous future foreclosed, destined either to be swallowed or to be blown apart. It never had a chance at the long, quiet life its nature would otherwise have promised. It is, in a sense, a star that will die young twice over, first losing its future to the inspiral, and then losing its existence to the giant, and it keeps faithful time for the giant the whole way down, sweeping the dust, marking the 6-year beat, right up until the end. So think about what we are actually looking at when we look at Betelgeuse now. We're not looking at a lone star dying quietly in the dark. We are looking at a system, a pairing, a small drama playing out across 600 light-years. A monstrous, bloated giant in the final chapter of its life, burning through the last rungs of its fusion ladder toward the iron that will end it. And circling it, a young star in the prime of its life, driving the giant's 6-year heartbeat and slowly falling toward its own destruction inside the giant's outer shells. Two stars, one old and one young, both doomed, one racing toward a supernova from within, and the other spiraling toward being swallowed from without. The dying giant will not die alone. It will take its companion down with it. And this reframes the whole story, because for centuries we thought of Betelgeuse as a single point of orange light, a lone ember on the hunter's shoulder. Now we know it is something richer and stranger, a dying star with a doomed partner, a slow tragedy unfolding in 2 acts at once. The great dimming showed us that the giant is unstable and shedding pieces of itself. The discovery of Betelgeuse showed us that it is not alone, that it has a companion it is destined to consume, and that even the rhythms we thought we understood were being driven by a hidden second star all along. Every time we look closer at Betelgeuse, it turns out to be more active, more violent and more alive with drama than we knew. But through all of it, through the dimming and the companion, and the shedding and the churning, one question keeps rising back to the surface. The same question that sent telescopes scrambling in 2020. The same question that hangs over every twitch and flicker of this star. We know how Betelgeuse will die. We know it will climb to iron and collapse in a single second and tear itself apart. We know it will not die alone, but we do not know the one thing everyone most wants to know. We do not know when. And the fight over that single question, the fight over when Betelgeuse will explode, has divided some of the sharpest minds in astronomy against each other. Part 6. The Fight Over the Clock. When will Betelgeuse explode? It is the most natural question in the world, and it is the one question no one can truly answer. Let me give you the honest, frustrating, wonderful truth first, and then we will get into why. The honest truth is that the explosion of Betelgeuse could happen tonight. It could happen while you are listening to these words. The core could already have collapsed, and we simply cannot see it yet. Or it could happen 10,000 years from now, or 50,000, or 100,000, long after every language spoken today has been forgotten, long after everyone alive right now is gone, and their descendants have become strangers to us. Somewhere in that enormous window, from tonight to 100,000 years from now, Betelgeuse will die. And no scientist on Earth can narrow it down more than that with any certainty. That is not a failure of intelligence, it is the nature of the problem. But within that huge window, there is a genuine and fascinating scientific fight going on right now about where the truth actually lies, and it pits two camps of astronomers directly against each other. To understand the fight, you have to understand why the timing is so hard to pin down in the first place, everything that matters is hidden. The whole drama of a star's death, the climbing of the fusion ladder, the building of the iron core, the final countdown, all of it happens far down in the center of the star, sealed away beneath hundreds of times the width of our sun of churning gas. We cannot see the core of Betelgeuse. No telescope can. Light from the core does not simply travel out and reach us. It gets absorbed and re-emitted countless times on its way up through the layers, so that by the time it reaches the surface, all the direct information about what is happening at the center has been scrambled and lost. We are trying to diagnose a patient whose vital organs we can never examine. All we get to see is the skin. So how do astronomers try to figure out which rung of the ladder Betelgeuse is on right now? They do it indirectly, by reading the outside of the star and running it through computer models of how stars evolve. They measure the star's brightness, its temperature, its size, the way it pulses and shakes. They feed all of that into simulations built on the physics of stellar interiors, and they ask the simulations, essentially, what would a star have to be doing inside to look like this on the outside? It is clever, it is powerful, and it is exactly the kind of reasoning that has taught us almost everything we know about stars. But it has a weakness, and the weakness is this. The same outer appearance can sometimes be produced by more than one in a state, and that is precisely where the fight breaks out. On one side, there is a group of astronomers, including a team working in Japan, who have looked at the pulsations of Betelgeuse in detail and come to a startling conclusion. They argue that the way Betelgeuse is pulsing, the specific rhythm and timing of its swelling and shrinking, is best explained if the star is already burning carbon in its core. Remember the ladder. Carbon burning is one of the very last stages. It is the rung after helium, and it lasts only centuries. If this group is right, then Betelgeuse is not somewhere in the comfortable middle of its old age. It is in the final stretch. By their reckoning, the carbon in the core could be exhausted within roughly the next few hundred years, and once the carbon is gone, the remaining stages, the neon and the oxygen and the silicon, blow past in years and months and days, until the iron core forms and collapses. In their scenario, the supernova follows within a few tens of years of the carbon running out. In the coldest reading of their argument, that puts the death of Betelgeuse potentially within centuries, a blink in cosmic time, close enough that it stops feeling abstract. It is a genuinely provocative claim, and it made headlines precisely because it dares to suggest that this might be something our own civilization, not some far future one, could witness. But on the other side, there are astronomers who look at the very same star and reach a far more relaxed conclusion. A separate group, working in Hungary, along with the results of other careful modelling, argue that Betelgeuse is nowhere near that close to the end. They read the evidence as pointing to an earlier stage, the helium-burning phase, the one that comes long before carbon, the one that still has hundreds of thousands of years left to run. And this reading got significant support from another line of research entirely. A few years ago, a careful study led out of Australia went back and remeasured the fundamental properties of Betelgeuse, its true size and its true distance, and found that the star is actually somewhat smaller and somewhat closer to us than many older estimates had assumed. And a smaller, closer Betelgeuse fits most naturally with a star still in that earlier, more stable helium-burning stage, a star with tens of thousands of years still ahead of it, not a star on the doorstep of death. In this reading, the supernova is real and it is coming, but it is a problem for a civilization far in our future, not for us. So there you have it. Two groups of serious, capable astronomers looking at the same orange point of light and disagreeing by a factor of hundreds or thousands about how long it has left. One camp says the clock may be down to its final centuries. The other says there are tens of thousands of years left on it. And the reason they can disagree so wildly is that single, stubborn, unavoidable fact. Nobody can measure how much carbon is left in the core, because nobody can see the core. The most important number in the entire question, the amount of fuel remaining at the centre of the star, is a number we simply cannot read from the outside. We are left arguing about the interior of a sealed giant from the flickers on its surface, and honest, brilliant people come to opposite conclusions. The main tool in this fight is the star's own pulsation, and it is worth understanding why it can point two ways at once. When a star swells and shrinks in a regular rhythm, the exact timing of that rhythm depends on the star's internal structure, on how its density and pressure are arranged all the way down. In principle, This is a powerful clue, almost like listening to the tone of a bell to work out its size and shape without ever touching it. A big loose bell rings with a low, slow note. A tighter one rings higher and faster. Betelgeuse rings, in a sense, and astronomers read the period of its main pulsation and its longer secondary rhythms as notes that tell them something about the star inside. But here is the catch. To turn that ringing into an age, into a position on the fusion ladder, you have to run it through a model of the star, and the model depends on assumptions, including that troublesome, unmeasurable question of what is happening in the core. Feed in one reasonable set of assumptions, and the same pulsation says the star is in late carbon burning, nearly finished. Feed in another equally reasonable set, and it says the star is in comfortable helium burning, with ages of time to spare. That is the whole fight in a nutshell. Both camps are listening to the same bell, both are hearing the same notes, and because the interior of the star is hidden, because the one number that would settle it cannot be measured, they translate those notes into completely different verdicts about how long Betelgeuse is left. It is a reminder of how genuinely hard this problem is, and of how much we are still working at the very edge of what we can know. This is not settled science being reported to you as fact. This is a living argument happening now among people at the top of their field over a star you can walk outside and see tonight. I find something strangely beautiful in that. It is not a failure, it is a frontier. It means that when you stand in your backyard and look at Betelgeuse, you're looking at a genuine, live, unsettled mystery, one that the smartest people alive are still fighting over, and it means that nobody, not one person on Earth, can promise you that Betelgeuse will not explode tonight. The bold camp might be right, the cautious camp might be right, but even the cautious camp cannot rule out that the collapse has already begun, because of that hidden core and that long delay. Every clear winter night that you can see Betelgeuse is a night on which it might, just possibly, already be gone. And this brings us to one of the most remarkable pieces of the whole story, which is how we will actually find out when it happens. Because when Betelgeuse finally does collapse, the very first sign will not be light. It will be something far stranger and far faster. Remember what happens in the collapse. When the iron core gives way and crushes down into a ball of neutrons, it releases that unimaginable flood of ghostly particles, the neutrinos. And neutrinos have an almost magical property. They barely interact with matter at all. They pass through solid rock, through entire planets, through the outer shells of the dying star itself, as though none of it were there. Trillions of them are passing through your body right now from the sun, and you feel nothing. So when the core of Betelgeuse collapses, the neutrinos escape the center of the star instantly and stream outward at nearly the speed of light, passing straight through all those hundreds of solar radii of gas without slowing down. But the light of the explosion, the visible flash, cannot do that. The shock wave that produces the visible supernova has to fight its way up through all those layers of the star, and that takes hours. So the neutrinos get a head start. They leave the moment the core dies, and the light leaves hours later. Which means that here on Earth, the neutrinos will arrive first. There are detectors buried in mines and under mountains and far beneath the ice, enormous instruments built specifically to catch the faint whisper of neutrinos, and they are all connected in a global early warning network. When Betelgeuse collapses, those detectors will suddenly light up with a burst of neutrinos from the direction of Orion, hours before anyone sees a single photon of the explosion. The first sign that Betelgeuse has died will be a silent pulse of ghost particles sweeping through the Earth, tripping alarms in detectors around the world, giving astronomers a precious few hours of warning to swing every telescope they have toward the hunter's shoulder and get ready. It is one of the few times in all of science where we would get an advance warning of a cosmic event, a heads-up delivered by particles that have already passed through the dying star and the entire planet before the light even arrives. Think about what that moment would feel like. Somewhere, a detector far underground registers a sudden flood of neutrinos. An automated alert goes out. Astronomers everywhere get the message, and they know with certainty that the star died hours ago, that the light is already on its way, that within hours the sky itself is going to change. And then they wait, and they watch that familiar orange point on Orion's shoulder, knowing what is coming, knowing that the giant is already gone, waiting for the light of its death to finally cross the last stretch of space and reach us. Because when that light does arrive, It will not be a subtle thing. It will not be a slightly brighter star. It will be a spectacle unlike anything any human being has ever witnessed in all of recorded history. Part 7. The Funeral We Will Watch from a Safe Distance. So let us imagine it. Let us imagine the night the light finally arrives. The warning has come and gone. The neutrinos have swept through the Earth. Astronomers are watching, cameras are ready, and the whole world has been told to look up. And then, on the shoulder of Orion, where that quiet orange ember has burned for all of human memory, a new light begins to grow. At first it brightens quickly, over hours, climbing past every other star around it. It passes the brightness of the brightest stars in the sky. It keeps going. It passes the planets. It keeps going. Within a day or so, that single point of light on Orion's shoulder is burning brighter than anything in the night sky except the moon itself, a savage white point so intense that it hurts to look at directly, blazing where a dim orange star used to be. And it does not stop at merely being the brightest star. At its peak, the supernova of Betelgeuse is expected to shine roughly as brightly as the full moon, and perhaps brighter, all of that light concentrated into a single point rather than spread across a disk. Think about what that means. A single star, bright enough to rival the full moon, but compressed into one blazing pinprick. It would be easily, obviously visible in broad daylight, a fierce white star hanging in the blue afternoon sky, plainly there next to the sun, impossible to miss, impossible to explain away. People would step out of their homes in the middle of the day and see a second brilliant light in the heavens, and at night this new star would be so bright that it would cast shadows. Your own shadow, thrown on the ground at midnight, not by the moon, but by the death of a star 600 light-years away. You could read by its light. It would banish true darkness from the night side of the Earth for weeks. Try to imagine living through those weeks. Every single night you would step outside and there it would be. That impossible new star, brighter than anything else in the sky, hanging over the world. Every culture on Earth would be looking at the same light at the same time. It would be photographed billions of times. It would be the only thing anyone talked about. Children born that year would grow up and for the rest of their lives remember the season when a star exploded in the sky, the way we remember the great events of our own time. It would work its way into art and music and memory, and for those weeks, the whole of humanity, every nation and every faith and every language, would share one experience in common. All of us, small figures on one small planet, looking up together at the death of a giant. There is something almost unifying in that thought. A rare moment when the entire species would be doing the same thing, feeling the same wonder and the same unease at the same time. And then, slowly, it would begin to fade. Over weeks, and then months, the brilliant new star would dim, sliding back down through the ranks of brightness, until eventually it fell below what the naked eye could see, and the point on Orion's shoulder went dark for good. The hunter would be left without his shoulder star. Generations that came afterward would look up at an Orion that was missing something, a gap where the orange ember used to be, and only the old records and images would remember that a star had ever burned there at all. The constellation we have known our entire lives would be permanently, visibly changed, and everyone who lived through the explosion would carry the memory of the sky the way it used to look, and it would linger. This would not be a flash that comes and goes in a moment. The supernova would blaze at its tremendous brightness for weeks, then slowly, over many months, fade. For a season, the human race would live under the light of a dying star, a brilliant new point in the sky that everyone on Earth could see, that every culture would witness together, that would hang over every city and every ocean and every desert on the planet at once. It would be, without any competition, the most spectacular astronomical event in the entire history of our species. Nothing recorded, nothing witnessed, nothing painted or written about in all of human history would come close. And behind that beauty is a violence almost beyond description. In the single instant of its collapse, Betelgeuse will release more energy than our sun will produce over its entire 10 billion year lifetime. Let that comparison land. Everything our sun will ever do, every sunrise it will ever bring, every ray of warmth it will give across 10 billion years, Betelgeuse will exceed all of it in a single moment, in one convulsion of its dying core. The light of that death will spread outward through the galaxy, and it will be visible not just from Earth, but from half the Milky Way, a beacon announcing across thousands of light years that one of the great stars has fallen. Any astronomer on any world within a huge stretch of the galaxy would see it and know that something enormous had just died. And what would be left behind when the light finally fades and the funeral is over? Two things. The first is the expanding wreckage of the star, the outer shells blown off into space at a fraction of the speed of light, a growing cloud of glowing gas seeded with all the elements the star forged in its life, carbon and oxygen and silicon and iron, spreading out across light years, a beautiful, tattered remnant that would glow in our telescopes for thousands of years to come. And the second thing left behind would be the core. Remember that ball of neutrons, that city-sized object of impossible density that formed in the instant of collapse. That would remain a neutron star, one of the strangest objects in the universe, a sphere the size of a city holding more mass than our sun, spinning in the dark where a giant used to be. The orange ember on the hunter's shoulder would be gone forever, and in its place, invisible to the naked eye, would sit its crushed and glittering corpse. Now, at this point, a very natural fear tends to rise up. If this is such an unimaginably violent event, if a single star can outshine the galaxy and blaze in our daytime sky, then surely we should be worried. Surely something that powerful, going off in our cosmic neighborhood, must be dangerous to us. Surely a blast like that could harm the Earth, could burn the sky, could threaten life itself. It is the obvious question, and it deserves a real answer, because the answer is one of the most reassuring facts in this entire story. But it is also a fact that has been twisted and exaggerated more than almost anything else about Betelgeuse, and to understand why we are safe, we need to look honestly at what a nearby supernova can and cannot do. Part 8. Should we be afraid? Let me give you the bottom line first, plainly, so you can relax and simply enjoy the rest of this. Betelgeuse is no threat to Earth. When it explodes, it will be beautiful and it will be harmless. It cannot hurt us. And I want to walk you through exactly why, because the reasons are solid, and because there is a lot of nonsense out there that deserves to be cleared away. A supernova is genuinely dangerous, but only if it goes off close enough. Astronomers who study this have worked out roughly how near a supernova would need to be to seriously threaten life on Earth, mainly by damaging our protective ozone layer with a flood of high-energy radiation and cosmic rays. The distance that keeps coming up is somewhere under about 50 light-years, with some estimates stretching that danger zone out toward 100 light-years for the very worst effects. Inside that range, a supernova could strip away enough of the ozone layer to let harmful radiation reach the surface, disrupt the base of the food chain, and cause real ecological damage. That is the kind of event that some scientists have wondered about as a possible contributor to ancient mass extinctions in Earth's distant past. So the danger is real, in principle. It helps to understand exactly how a close supernova would do its harm, because it is not the way most people imagine. The danger is not that the blast would physically scorch the Earth or set the sky on fire. Even a fairly nearby supernova is still far too distant for that. The real threat is subtler and works through our atmosphere. A supernova pours out a tremendous flood of high-energy radiation and fast-moving particles, and if enough of that reached us, it would tear apart the molecules in our upper atmosphere that make up the ozone layer. The ozone layer is our invisible shield, the thing that absorbs the harshest ultraviolet radiation from our own sun before it can reach the surface. Strip that shield away, and the sun's own ultraviolet light would begin to damage life at the base of the food chain, the tiny organisms in the oceans and the plants on the land that everything else depends on. The supernova would not kill us directly. It would knock out our shield and let our own sun do the damage over the following years. That is the mechanism people are really talking about when they discuss the danger of a nearby star exploding. But every part of that mechanism depends on intensity, on how much radiation actually arrives, and intensity falls off dramatically with distance. Light and radiation spread out as they travel, thinning as they go, so that the same blast that could shred our ozone at 50 light-years arrives at 600 light-years, so weakened and so diluted that it cannot do the job. By the time Betelgeuse's radiation crosses all that space and reaches us, it is a gentle thing, easily handled by an atmosphere that deals with far worse from our own sun every day. The shield holds. Nothing is stripped, nothing is harmed. The distance that makes Betelgeuse so poignant is the very same distance that makes it completely safe. But now look at where Betelgeuse actually is. Betelgeuse is around 640 light-years away. Even by the more recent measurements that place it closer, it is still well over 500 light-years from us. That is more than 5 times, and probably more than 10 times, farther than the distance at which a supernova could do us any harm. Betelgeuse is not in the danger zone. It is not anywhere near the danger zone. It is so far outside it that when its blast of radiation finally arrives, spread thin across all those hundreds of light-years, it will be so diluted that it will do nothing to us at all. Our atmosphere will absorb it without trouble. The ozone layer will not notice. Not a single living thing on Earth will be harmed by the death of Betelgeuse. The energy that would be lethal at 50 light-years is, at 600, simply a light show. For us, the death of this giant will be pure spectacle and zero threat, the most violent event we could ever witness, rendered completely safe by the one thing that also makes it so poignant, the enormous distance in between, so that is the truth. Now let me deal with the stories, because whenever Betelgeuse does anything, the internet fills up with claims, and it is worth looking at them honestly and saying clearly where the real science stands. This channel does not pretend these theories do not exist, and it does not just mock them either. Let us actually look. The first claim, which surged during the Great Dimming, was that the fading was the supernova beginning, and that scientists knew and were keeping it quiet to prevent panic. We have already seen the reality. The dimming was caused by a cloud of dust from a surface mass ejection, and this was not hidden by anyone. It was studied in the open by observatories around the world, by amateur astronomers in their backyards, and published in the scientific literature for anyone to read. There was no cover-up because there was nothing to cover up, and even if there had been, the data were in thousands of independent hands. The idea of a secret does not survive contact with how astronomy actually works. The second claim goes further. It says that Betelgeuse has already exploded, and that this fact is being concealed from the public. Now here the physics itself makes the claim impossible, and it is worth understanding why, because it is genuinely elegant. When Betelgeuse explodes, the signal does not arrive at one secret government telescope that can bury it. The neutrinos sweep through the entire Earth and trip detectors on multiple continents at once. The light, when it comes, floods the whole night side of the planet. Every astronomer, every observatory, every amateur with a camera, in every country, friendly and unfriendly, would see it in the same hour. You cannot hide a light bright enough to cast shadows and be seen in daylight across the whole world. The reason we will not know until the light arrives is not secrecy. It is distance. It is the simple, honest fact that the news is still in transit. Those are two completely different things, and it matters to keep them straight. The third claim is the scariest sounding one, that a nearby supernova will fry the Earth, flip the magnetic poles, trigger mass extinction, end civilization. And we have already dismantled it with a single number. Betelgeuse is far, far outside the distance at which any of that could happen. A supernova that went off within 50 light-years might indeed do terrible things to the biosphere. Betelgeuse is more than 10 times farther than that. It cannot flip our poles, it cannot burn our sky, it cannot end anything. The doomsday version of this story takes a real danger that applies only to very close supernovae and falsely staples it onto a star that is nowhere near close enough. The truth is less frightening and, honestly, more wonderful. We get all of the spectacle and none of the harm. And the last claim is a quieter one, that the companion star, Betelgeuse, was known about for a long time and deliberately hidden until recently. The reality is simply that it was genuinely, extraordinarily difficult to see. We are talking about spotting an ordinary star buried in the glare of an object hundreds of millions of times brighter, across 600 light-years. It took a specialized instrument on one of the most capable telescopes on Earth, pushing right at the limit of what is physically possible, to pull that faint companion out of the light. It was not concealed. It was just genuinely, technically, one of the hardest observations in modern astronomy, and the moment it was confirmed, it was announced to the world. So when you strip it all away, what you find is that every dramatic claim about Betelgeuse turns out to have a grounded, honest explanation, and that the reality is stranger and more interesting than the conspiracy. The star really is unstable. It really is shedding pieces of itself, It really does have a doomed companion. It really is going to explode. Those things are all true, and they are all extraordinary, and none of them require a secret or a cover-up to be amazing. The universe is dramatic enough on its own. It does not need our embellishments. But here is something worth sitting with now that we know we're safe to simply watch. We would not be the first human beings to look up and see a star die. Far from it. Across the long span of our history, our ancestors looked up on certain rare and unforgettable nights, and saw new stars blaze into being where none had been before, and though they had no idea what they were looking at, they were watching exactly the same kind of death that waits for Betelgeuse, and the records they left behind reach across the centuries to meet us. Part 9. The Ghosts of Dead Stars. In the summer of the year 1054, astronomers in China looked up and recorded the sudden appearance of what they called a guest star. It arrived without warning, in the constellation we now call Taurus, and it was astonishingly bright. According to the records that survive, it was brilliant enough to be seen in broad daylight for over 3 weeks, a fierce new point of light hanging in the daytime sky, and it remained visible at night for nearly 2 years before it slowly faded away and was gone. The court astronomers of the time dutifully wrote it down, this strange visitor that appeared and then vanished. Sky watchers in Japan and in the Arab world noted it too. They did not know what it was. They had no concept of a star dying, no idea of iron cores or collapse or supernova. They only knew that a new light had come, blazed, and departed, and they recorded the fact and passed it down. We know exactly what they saw. If you point a telescope today at the spot in Taurus where that guest star appeared, you will find a beautiful tangled cloud of glowing gas called the Crab Nebula, still expanding outward almost 1,000 years later, and at its centre, a spinning neutron star, the crushed core left behind by the collapse. What the astronomers of 1054 witnessed was a supernova, the death of a massive star, the very same kind of event that is coming for Betelgeuse. They watched a star die, wrote it down without understanding it, and left us a record that we can now read with full knowledge of what it truly was. Their guest star was a funeral, and they attended it without knowing. And it was not the only one. Our ancestors witnessed several of these across recorded history, each one a rare and startling event. In the year 1006, less than 50 years before the Crab, an even brighter new star appeared, so brilliant that observers scattered across the world. In China, in Egypt, in Europe, in Japan, all recorded it, and by some accounts it was bright enough to read by at night. It is remembered as the brightest stellar event in all of recorded history. Then, centuries later, in 1572, a new star blazed forth and was studied by the astronomer Tycho Brahe, and its appearance helped shatter the old belief that the heavens were fixed and unchanging, because here, plainly, was change, a new star where none had been. And then, in 1604, just a few decades later, another one appeared, observed and recorded by Johannes Kepler, one of the founders of modern astronomy. And then they stopped. That supernova of 1604, the one Kepler watched, was the last supernova in our own galaxy that human beings have seen with their naked eyes. Since then, for more than 400 years, we have not witnessed a single star die within the Milky Way with our own eyes. We have seen distant ones in other galaxies, faint points that flare in our telescopes and fade, millions of light years away. But a close one, a bright one, a guest star blazing in our own sky, the kind our ancestors saw, we have not had one since before the telescope was even fully invented. Kepler watched his new star with his eyes alone, and no human being since has seen its like in our galaxy. Now here is what makes that a remarkable fact. Supernovae are not supposed to be that rare in a galaxy like ours. Astronomers estimate that a galaxy the size of the Milky Way should produce something on the order of a few supernovae every century, a few every 100 years. And yet we have gone more than 4 centuries without seeing one nearby. Where are they? Some of them almost certainly have happened, but hidden from us, on the far side of the galaxy, their light smothered by the thick clouds of dust that fill the plane of the Milky Way so that the flash never reached our eyes. We may have missed them behind the dust. In fact, we have good reason to believe exactly that happened. There is a beautiful tattered remnant of an exploded star in the constellation Cassiopeia, a great expanding shell of glowing debris that astronomers have studied in enormous detail. By measuring how fast that shell is expanding and running the clock backward, We can work out roughly when the star that made it must have exploded, and the answer comes out to somewhere around 350 years ago, which places the explosion in the late 1600s. And yet, astonishingly, there is no clear, confident record of anyone on Earth seeing it happen. A star died in our own galaxy, relatively nearby, within the age of telescopes, and it seems to have gone off almost unnoticed, its light heavily dimmed by the dust between us and it, so that at most it appeared as a faint, forgettable star that drew no attention. A supernova happened in our cosmic neighbourhood, and humanity very nearly slept through it. That is how effective the dust can be at hiding these deaths from us. So the historical record of guest stars, dramatic as it is almost certainly incomplete. There have been more deaths than we saw, more giants that fell behind the curtain of dust without ever lighting up our skies, which makes the ones we did see, the guest stars of 1006 and 1054 and 1572 and 1604, all the more precious. The rare cases where a dying star happened to be positioned in a clear enough line of sight for its light to reach us unobscured. And it makes the prospect of Betelgeuse all the more extraordinary, because Betelgeuse sits in a clear part of the sky, close and unhidden, with no great bank of dust between us and it to steal the show. When Betelgeuse goes, there will be no missing it. There will be no sleeping through it. It will not be a faint smudge that historians puzzle over centuries later. It will be the brightest and most unmistakable stellar death in the entire history of our species, staged in the clear, right where all of us can see. But the arithmetic still leaves many people with the strong sense that we are, in a way, overdue, that the galaxy is due to give us another guest star, another naked-eye death, another light in the daytime sky. And when it comes to nearby candidates, to stars close enough and massive enough, and far enough along to give us that gift, one name sits at the very top of nearly everyone's list, Betelgeuse. Because think about how it compares to those historical events. The guest star of 1054, the Crab, was thousands of light years away, and still it burned in the daytime sky for weeks. The supernova of 1006 was also far more distant than Betelgeuse. Every one of those famous historical supernova, the ones that stunned our ancestors and got written into the chronicles of empires, went off much farther away than Betelgeuse is now. Betelgeuse, at 640 light-years, would be the closest supernova humanity has ever knowingly witnessed. It would not merely match the guest stars of old, it would utterly eclipse them. It would be dramatically brighter than the Crab, brighter than Kepler's star, brighter than anything in the written memory of our species, precisely because it is so much nearer. The astronomers of 1054 saw a candle across a stadium. We would be watching one held up across a room. The difference in nearness is the difference between a curiosity noted in a chronicle and an event that would stop the entire world in its tracks. No one who lived through it would ever forget it, and no one who came after would be able to imagine the sky the way it had been before. And there is one more difference between us and them, and it may be the most important of all. When the astronomers of 1054 saw their guest star, they had no idea what it was. They saw a light appear and vanish, and they could only wonder. When Betelgeuse goes, we will not merely see it, we will understand it. We will know that we are watching an iron core collapse, that we are seeing the birth of a neutron star, that the elements forged in the giant's long life are being scattered into space before our eyes. We will point instruments across every kind of light at it, catch its neutrinos, measure its expanding debris, and read the death of a star in a detail no human generation has ever been able to bring to bear. Our ancestors watched a mystery. We will watch a known thing, in full, and it will still leave us speechless. So when you stand outside and find Betelgeuse on the hunter's shoulder, you're looking at the same kind of object that appeared as a guest star to the astronomers of 1,000 years ago, except this one has not gone off yet, and this one is close, and this one, when it dies, we will be ready for. We are living in the strange suspended moment before the guest star arrives, and that suspended moment carries with it the single strangest thought in this entire story. The thought we have been circling since the very beginning, the one that turns a simple point of orange light into something almost unbearable to contemplate. Part 10. The Star That May Already Be Dead. Here is the thought. Here is the one that changes how you will look at Betelgeuse for the rest of your life. The light you see when you look at Betelgeuse tonight left that star around 640 years ago. We have said this already, But now I want you to follow it all the way to its conclusion, because the conclusion is staggering. That light is old. It is a message that has been in transit for 6 centuries. And a message that takes 600 years to arrive can only ever tell you about the past. It cannot tell you about now. When you look at Betelgeuse, you are not seeing the star as it is. You are seeing the star as it was 640 years ago, and you have absolutely no way of knowing what has happened to it since. So think about what that means, given everything we now know. We know Betelgeuse is at the end of its life. We know it could be in its final centuries if the boldest astronomers are right. We know that when it collapses, it does so in less than a second without warning. And we know that the light of that collapse would take 640 years to reach us. Put those facts together, and you arrive at something that sounds like a riddle but is simply the truth. Betelgeuse may already be gone. Right now, in this very moment as you listen to this, the star may no longer exist. It may have collapsed and exploded 100 years ago, or 300 years ago, or last century, and the light of its death may be somewhere out there in the dark right now, crossing the final stretch of space between it and us, still on its way, not yet arrived. Every night that you look up and see that orange point burning on the hunter's shoulder, you are seeing light that is already old, from a star that may already be a corpse, a neutron star sitting in an expanding cloud of its own wreckage, while the last of its living light, sent out centuries ago before the end, continues to pour toward you across the emptiness. The ember you see may be a ghost. The star may have died in the age of sailing ships, and we would still see it glowing tonight, because the news of its death simply has not finished travelling yet, and we would not know. We could not know. There is no way to check. There is no faster signal we could send to go and look. The only thing that can tell us Betelgeuse has died is the arrival of the light and the neutrinos from that death, and those things travel at their own fixed speed and cannot be hurried. So we are left in a genuinely strange situation, suspended in ignorance by the sheer size of space. The explosion could already have happened. The flash could already be racing toward us. The shockwave of neutrinos could already be crossing the last light years, and one night, without any warning, the detectors could ring and the sky could change. Or it could be 1,000 years away, or 10,000. And from where we stand, watching that patient orange light, all of those possibilities look exactly the same. There is no difference to our eyes between a Betelgeuse that has centuries left and a Betelgeuse that died 300 years ago and whose final light is arriving next Tuesday. They both look like the same quiet ember. I find this to be one of the most profound ideas in all of astronomy, and it is not a trick or an exaggeration. It is just what it is like to look at the universe across enormous distances. The night sky is not a snapshot of the present. It is a collage of different pasts, each star showing you a different amount of time ago, the near ones nearly current, the far ones deeply historical, all of it stitched together into a single dome that looks deceptively like one moment. When you look up, you are looking across time as much as across space. And Betelgeuse is the most dramatic example of that truth that we can easily point to, because it is a star we know is dying, near enough to matter, far enough that its present is completely hidden from us behind 6 centuries of travel time. There is a particular kind of vertigo in that. Stand outside on a cold, clear night. Find Orion, trace the belt, look up to the shoulder, and settle your eyes on that single orange point. And as you look at it, hold in your mind the full weight of what you might actually be seeing. You might be looking at a living star, ancient and enormous, still burning through the last of its fuel, with centuries or millennia still to go. Or you might be looking at the lingering light of something that is already gone, a farewell sent centuries ago still arriving. You cannot tell which. Nobody can. And there is something almost sacred in that uncertainty, in standing on the surface of a small planet and looking up at a light that may be a living giant or may be the ghost of one, with no way to know and no choice but to simply look and wonder and wait. Because in the end, waiting is all we can do. We cannot make Betelgeuse explode, and we cannot stop it, and we cannot even find out whether it already has. All we can do is watch and understand and appreciate that we happen to be alive at a moment when the nearest dying giant hangs in our sky, primed, ready, its fate already sealed one way or another, its final light either still to come or already on its way. We are the generation that gets to look up and know what that orange ember truly is, and know what is coming for it, and know that we might, on any given night, be the ones who get to see it go. But if this story ended only in death, only in collapse and ghosts and the long cold wait, it would be missing the most important part of all. Because the death of a star like Betelgeuse is not only an ending, it is also, strangely, gloriously, a beginning. And to see why, we have to follow the wreckage of the explosion outward, into the dark, and discover where it goes, and what it becomes, and why the death of this one giant is woven directly into the story of how you came to exist at all. Part 11. What the dying giant gives back. Think back to the fusion ladder, to all those elements building up inside Betelgeuse across its life. Hydrogen fusing into helium, helium into carbon and oxygen, carbon into neon. On and on, up the ladder, forging heavier and heavier elements in the furnace of the core all the way to iron. That process has a name. Astronomers call it nucleosynthesis, the building of the elements inside stars, and it is not just a piece of trivia about how stars work. It is the origin story of everything, including you. Because when the universe was young, it contained almost nothing but the two lightest elements, hydrogen and helium. That was very nearly the entire menu of creation. There was no carbon to build living things from, no oxygen to breathe, no nitrogen for the air, no silicon for rock, no iron for blood or for the cores of planets. None of it existed. The universe was a thin soup of the two simplest ingredients, and nothing else. So where did all the rest of it come from? Where did the carbon in your body come from, the oxygen in every breath, the calcium in your bones, the iron in your blood? The answer is that it came from stars. It came from generations of giant stars that lived and forged these elements in their cores, and then died and scattered them into space. It came from Betelgeuse, or rather from stars exactly like Betelgeuse that came before it. This is the part that gives the death of a giant its real meaning. When Betelgeuse explodes, it does not simply destroy itself and leave a corpse. It takes all of those elements it spent its life forging, the carbon and oxygen and silicon and iron, and it blasts them outward into space at a fraction of the speed of light. The explosion becomes a seeding. That expanding cloud of enriched debris spreads across light years, mixing into the great clouds of gas and dust that drift between the stars. And those clouds are the nurseries where new stars are born. So the material of the dying giant becomes the raw ingredient for the next generation. New stars condense out of that enriched gas, and around those new stars planets form, planets made possible only because a previous giant died and gave up its elements. Rocky worlds, with iron cores and oxygen in their crusts and carbon on their surfaces, worlds that could never have existed in the empty early universe. Worlds that exist only because giants like Betelgeuse lived and died and gave their substance back to the dark. And on at least one such world, those scattered elements came together in a way that could get up and look at the sky. That is not poetry. It is chemistry and history. The atoms that make you were forged inside stars that died before the sun was born. The iron carrying oxygen through your blood right now was made in the core of some ancient giant and flung into space by its death. The calcium holding you upright, the carbon that forms the backbone of every molecule in your body, the oxygen filling your lungs at this moment, all of it was cooked inside dying stars and scattered by explosions like the one waiting for Betelgeuse. You are, quite literally, made of the ash of dead giants. You are the universe's way of remembering the stars that came before. So when we watch Betelgeuse and wait for its death, we're not only watching an ending, we are watching the exact process that made us, playing out again in real time, close enough to see. That expanding cloud of debris that Betelgeuse will one day become is the same kind of cloud that, billions of years ago, helped build the sun and the earth and everything on it. Betelgeuse, in dying, will hand its forged elements to the future, to new stars and new worlds that will form long after we're gone, and perhaps, someday, to new living things that will be built from its atoms and will look up at their own sky and wonder where they came from. The death of the giant is a gift to whatever comes next. Destruction and creation turn out to be the same act, seen from different ends of time, and that, in the end, is the real story of the orange ember on the shoulder of Orion. It is a giant so enormous that our whole world could vanish inside it. It is a star burning through the final rungs of its life, building iron in its core, marching toward a collapse that will take less than a second and outshine the galaxy. It is a star that has already shivered and shed pieces of itself, that carries a doomed young companion spiraling toward its embrace, whose exact time of death divides the sharpest minds we have. It is a star so far away that its light is centuries old, so that it may already be gone and we simply do not know. And it is a star whose death, when it comes, will not only be the most spectacular light in the history of our species, but will also be a seeding of the future, scattering the very elements that make worlds and make life, an ending and a beginning, folded into one point of orange fire. So the next time you step outside on a cold, clear winter night, do this. Find Orion. Find the 3 stars of his belt, look up to his shoulder and find that single point of orange light, and then just hold the moment. Hold it, and remember what you are looking at. You are looking at a dying giant, 1,000 times wider than the sun, 6 centuries of light away. You're looking at a star that has a doomed companion, and a hidden clock ticking in its core, and a death sentence already written. You may be looking at a living star with 100,000 years left, or you may be looking at the last light of something that died before you were born, a farewell still crossing the dark to reach you. You cannot know which. And one day, perhaps tonight, perhaps 10,000 years from now, long after everyone who has ever lived is gone, the universe will finish that message. The light will arrive, the sky will change, and the human beings alive on that night, whoever they are, will look up and watch a giant die. The only question the universe has left us is whether we will be the ones lucky enough and small enough and awake enough to be looking up when it finally happens.